Hello, everyone. Good morning, good afternoon, and good evening, wherever you may be in this world. I would like to welcome you to today's webinar, Unraveling the Charge Heterogeneity of Biotherapeutics, icIEF Fractionation for Mass Spectrometry Characterization. I'm Christy Jewell of Labroots, and I will be your moderator for today's event. Today's educational web seminar is presented by Labroots and brought to you by Bio-Techne. To learn more about our sponsor, please visit biotechne.com or click on that Bio-Techne logo at the bottom of your screen. Now, we could encourage you to participate today by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We will answer as many of your questions as we have time for at the end of the presentation. Additionally, you may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. Now, in addition to answering your questions, we have some questions for you. Please see the survey window at the left of your screen, and just below that, you will see a list of resources to further your Maurice journey. Be sure to check them out. And with that, I'd like to now welcome our speaker, Dr. Kefei Wang, Senior Product Manager at ProteinSimple of Bio-Techne. For a complete biography on our speaker, please visit the Biography tab at the top of your screen. Dr. Wang, welcome. You may now begin your presentation.
Hello, everybody, and good morning and good afternoon. Welcome to our Bio-Techne webinar operated by Labroots. Today's topic is Unraveling the Charge Heterogeneity of the Biotherapeutics. We'll discuss the icIEF fractionation for mass spectrometry characterization. First, we'll give you a brief overview of the icIEF technology and its application to the biotherapeutic charge heterogeneity characterization. Second, I'd like to introduce our newest Maurice Flex instrument featuring the icIEF fractionation technique. And this will be followed by two case studies. First, with the NIST map for the LC-MS intact mass and peptide mapping. The other, a therapeutic DVD-Ig drug for intact mass and the reduced mass analysis. icIEF stands for Imaged Capillary Isoelectric Focusing. The technique was invented in early 90s by Jiaqi Wu, then a postdoc work at the University of Waterloo. The principles of the icIEF is illustrated here. First, you load the background electrolyte, the PI markers, and the protein samples. This takes about 1 minute. Then, instead of using an end detector at the end of the capillary, the icIEF uses UV or fluorescence to shine on the whole capillary and the CCD camera on the other side to record the whole capillary images. So when voltage applied to the end of the capillary, the background electrolyte will create a pH gradient, and the PI markers and the proteins will be focused to form bands inside the capillary based on their PI values on the pH scale. Now remember that the whole process will be recorded on the CCD camera, so the detection goes simultaneously with the separation, which take about 10 minutes. So when the separation is completed, the last image will be just your final electrophoregraph. The icIEF has some distinct advantages over the traditional CIEF because it runs fast, as it does without the mobilization of the proteins to the end detector, which can take twice as long as the separation process. Second, it is of high resolution because it also does without the pressure mobilization of the protein bands inside the capillary. As we know, every time you're trying to move the bands inside the capillary using pressure, you're going to lose the resolution. And lastly, and perhaps more important, it is much easier for method development when you play with the separation parameters with icIEF, because each run is fast, and with imaging, what you see is what you get. So you can sort of monitor the focusing separation in real time and to know what works and what's not. Jiaqi set up his own company to make the icIEF instrument. And the first commercial icIEF instrument, the CE280, was introduced in 1999, and the company was later acquired by what is now ProteinSimple, a brand of Bio-Techne. And over the years, the icIEF instrument has gone through several generations of innovations. The ICE3, introduced in 2012 by ProteinSimple, was the industrial standard for protein charge heterogeneity analysis. So we had thousands of them in our customer laboratories. Now it has been replaced by Maurice since 2016, and Maurice is the current industry standard for charge profile analysis. Now note that the Maurice can run not only the icIEF, but also the CESDS. And early this year, we introduced a new sibling of the Maurice, Maurice Flex, with the fractionation capability, which is the topic of this presentation. Now, before we get on to the Maurice Flex, let's have a quick review of the Maurice analytical workflow. So here are the steps. First, you insert a cartridge, that is the Maurice analytical cartridge, into the Maurice instrument. Then you load the reagent and the samples. And then in your software, you set up the batch, which is like a sequence. You click the start button, the Maurice is going to start running, collecting the data, and you can analyze the data. So overall, it is a simple and fast workflow, which takes about 10 to 12 minutes per sample. And then the results are accurate and reliable. So all these had made the Maurice the current go-to platform for profile-based assay for the charge heterogeneity analysis, which is a critical quality attribute of the biotherapeutics. Now, one of the limitation of the icIEF and then the Maurice is that they cannot do the fractionation. So it cannot allow to collect the charge isomers for in-depth structure analysis. For example, if you want to use the mass spectrometry to investigate the source of the charge differences due to such as C-terminal lysine, PTM, and glycosylation, and etc. If you want to perform mass spec analysis on the charge variant, currently there are two strategies. The first is to use the ion exchange chromatographer, or IEX, for fractionation, and run the fraction samples with the mass spec. So this is the most often practiced, and IEX fractionation is known to be straightforward and with large capacity. Now, however, there are some difficulties with this approach. First and foremost, it's difficult for IEX charge profile to match that of the icIEF because the IEX separation mechanism is different than the icIEF. Now, for the ion exchange chromatographer, the separation is based on the interreaction of the surface charges of the protein with the column media. So it is not truly a PI based. Now, second, the IEX in general has a lower resolution than the icIEF because the peak broadening effect with the column chromatographer. Third, the IEX method development is in general time consuming because it is a try and error process. Now the second strategy is the direct coupling of the CE with the mass spec. Now this is a popular thought for any of the mass spec user, particularly if they are used to the direct coupling of the LC with the mass spec. Now in this direct CE-MS approach, you can measure the PI and intact mass, but it also has some severe limitations. First, the CE-MS direct coupling needs a special interface to couple the CE to the electrospray of the mass spec, and this interface is often vendor specific and even mass spec specific. Now, second, the CE flow to the ESI is in the lower nano to microflow range. So this is not a QC-friendly method and less robust. Also, some of the common CE additives, like the methylcellulose and the urea, cannot be used because they are incompatible with the electrospray of the mass spec. So you need to use other alternative reagent to redevelop your CE method. Last, this is for intact mass only. It cannot perform the reduced mass, subunit mass, and peptide mapping. Also, we need to understand that in laboratories, one does not need to run the fractionation all the time. Only when there is a project or there is an unexpected charge peak. So with all these in mind, we developed and introduced here a third strategy, a true PI-based icIEF fractionation with the Maurice Flex. So here are the main features of the Maurice Flex. So first, it is a Maurice instrument, runs the icIEF fractionation on a new fractionational cartridge. Now second, the fractionation method development are based on the analytical regular Maurice and icIEF method. So the method development with the fractionation is fairly easy. The third, the Maurice Flex runs all the existing icIEF and the CESDS assays just like a regular Maurice. So if it's not used for the fractionation, the Maurice Flex can be used just like a Maurice. So there's no need for method revalidation of those icIEF and SDS assays you previously run on the Maurice instrument. The last, the Maurice Flex runs on the same software platform that is the Compass for ICE as all other Maurice family members. So this will shorten the learning curve for running the Maurice Flex. So essentially, Maurice Flex is just a Maurice with the new fractionational feature. And the Maurice Flex can run the same Maurice assays using the same Maurice analytical cartridges. So what's different for the fractionation is that the fractionation run will use a special newly designed CIEF fractionation cartridge. And this cartridge can support up to 15 fractionation runs. Now we also have a new plate holder for 96 well plate to support this cartridge. And I would like to also mention that for fractionation run, we only use fluorescence for image detection. Now, for analytical runs, the Maurice Flex can still use both the UV and the fluorescence like a Maurice. It's just for the fractionation run, we only use the fluorescence detection. The key to the icIEF fractionation is the technique called chemical mobilization, which we're going to illustrate in this cartoon here. So this is the capillary. We first load the proteins and the electrolytes. We then apply the voltage, so a pH gradient will be formed, and the proteins we're going to start focusing into the bands inside the capillary. Now, once the protein getting focused, the next step, we are going to replace the basic catalyte solution with a neutral salt solution. Here we are using the ammonium acetate solution. So this will going to cause the pH changes inside the capillary. So the previously focused proteins are no longer focused. So they are going to move toward the cathode end. So one by one, they're going to elute out. Their fractions can be collected. So this is the principle of the chemical mobilization. The advantage of the chemical mobilization is that it can preserve the high resolution of the icIEF. So this is compared to the traditional CIEF mobilization with the pressure by pump. Now second, not only the charged molecules, like the protein charge variant, are mobilized and collected. The CE additives like methylcellulose and the urea are not mobilized because they are the neutral molecules. So Maurice Flex fractionation run can use the methylcellulose and the urea. So this is in contrast to the direct CEMS. In direct CEMS, the methylcellulose and the urea, if they are used, they will be pumped into the mass spec, but they are not compatible with the mass spec, so they cannot used in the direct CEMS. Now let's look at the Maurice Flex applications. So the first sample is the NISMAP. As we know, the NISMAP has been a common reference standard for evaluating analytical technology for the antibody characterization. So here we're going to apply the fractionation to the NISMAP and to get a charge variant for intact mass and the peptide mapping analysis. Now here are the experimental steps of the fractionation. The first step is the setup. We insert a fractionation cartridge and prepare the reagent and load the sample. Note that the NISMAP concentration is 1 milligram per ml. This step will take about 30 minutes. The second step is focusing. Here we use a 3-step focusing, which has a total time of 45 minutes. And after focusing, we run the mobilization. We are going to replace the catalyzed solution with the 5 millimole of ammonium acetate solution. We kept this at 1000 volts for 25 minutes. Now, after mobilization, we can start collect the fractions. We run the fraction collection on a 96 well plate, each fraction for each well. Total 36 fractions will be collected at 25 seconds per fraction. Note that the 36 and the 25 numbers can be changed based on your application. So for each fraction, we place 30 microliter of ammonium acetate solution in each well, and we kept this at 1000 volts. The total time for the fraction collection will be 20 minutes. So from setup to complete the fraction collection will take about 2 hours. So after we collected all the fractions, we are going to proceed to run the verification to verify the identity and the purity of the fractions. Here we pick 16 fractions to analyze on the regular Maurice to confirm the identity and the purity. So overall, we can get the charge variant fractions in a single day, from the fractionation 2 hours to verification 4 to 5 hours. Now here is the comparison of the analytical CIEF run and the fractionation CIEF run. So on the left is the E-gram of the analytical CIEF run of the NISMAP using a CIEF analytical cartridge. On the right is the fractionation icIEF run with the flex cartridge. You can see on the left-hand side, we clearly observe 5 charge variant, the 2 basic B1, B2, and 2 acidic A1, A2 along with the main. And from the peak area, we can determine the relative abundance of each of the charge variant. And note that the least abundant one, B2, has abundance approximately 1%. The concentration of the analytical run is 0.25 milligram per ml. And with this concentration, the total amount of proteins we loaded onto the cartridge is approximately 0.1 microgram. So on the right-hand side is the fractionation run with the flex cartridge. So you can see here, we also observe 5 charge variant here, but you can see that the values between each peak has been increased, showing that the resolution is lower. But we need to keep in mind that the fractionation cartridge is designed for the preparative purpose, not for analytical one. So for this purpose, we can load much higher concentration. Here, the total amount of the sample loaded will be about 6 micrograms. So the important for the fractionation is that we need to observe the same number of the charge variant, and they should be well separated on the PI scale, which is the case here. Now, early in the experimental steps, we mentioned that we collected a total of 36 fractions, but we only picked 16 fractions for the verification. These 16 fractions were picked because they contain all the charge variant. Obviously, we do not want to analyze all 36 fractions. That will take too much time. But how do we know which fraction to include for the verification. So we have a software feature called peak prediction in our campus software for the Maurice Flex. It uses the extrapolation of the peak mobilization in the capillary image window to estimate the time for each fraction to arrive at the range of the wells. Note that this is only for estimation, and to make sure we do not miss anything, we need to include a few extra fraction wells in the front and in the back to bracket. Now, alternatively, you can also use a fluorescence reader to locate the wells with the highest intensity, which is usually the main peak. And then you can add 6 or 7 fractions in the front and in the back to cover all the charge variant fractions. Now, either way, we choose to pick 16 fractions to run the verifications. Now, here are the results of the verification runs. The top electrophoregram is the run of the NISMAP as a reference standard, showing 5 charge variant peaks here. The rest of 5 electrophoregrams are the fractions that were found to contain the purest of each of the charge variant. As you can see, all 5 charge variant of the NISMAP can be fractioned with 100% purity. Now, after the verification, we sent these 5 samples for intact mass analysis on the LCMS. The system used is Vanquish UHPLC and the Q-Executive HF. Now, here are the results of the intact mass. On the left-hand side are the base peak chromatograms of all 5 charge variants. The right-hand side are their corresponding raw mass spectra. You can see here all 5 charge variants can be analyzed by intact mass. The spectral quality are quite good. And even for the least abundant one, the B2, at only 0.98%, we can see a very good peak and with high quality mass spectra. The deconvoluted mass spectra are shown here. And from the spectra, we were able to identify the following modifications. In B2 and B1, we observed the mass shift of 259 and 128 Dalton, which corresponding to the incompletely clipping of the 2 or 1 terminal license. And the A1, A2 are the mass shift likely from the glycations. So these modifications we observe here are consistent with the published studies by others on the NISMAP. The last experiment we run with the NISMAP is the peptide mapping. As we know, peptide mapping will require much more samples. It will be a challenge for a single fractionation run to provide sufficient sample for the sample prep. So here we pull the fractions of the same charge variant from 10 fractionation runs. The pulled fractions was lyophilized on a speed vac and reconstituted prior to the trypsin digestion. With the pulling of 10 fractions, we were able to get decent LCMS chromatograms of the peptide mapping on all 5 charge variants. The chromatograms of the B1 and A1 are shown here as example. The sequence coverage get from the peptide mapping are decent at 84 to 95% for most of the charge variant, except for the heavy chain of the B2 and the A2. Now, after we demonstrate the success with the NISMAP, we move to a real-world molecule. So the second case here is about the fractionation of a therapeutic dual variable domain immunoglobulin, or DVD-IG, for LCMS characterization by intact and reduced mass. The results here presented were taken from our latest poster at this year's ASMS in June. Here again, on the left is the analytical icIEF profile of the DVD-IG with 0.25 milligram per ml. And then from the analytical profile run, we can determine the relative abundance of each of the variant from P1 to P5. So the P4 and the P5 are of our particular interest because their relative abundance changed during the heat stress test. Now, on the right-hand side is the fractionation icIEF run with 2 milligram per mil. As you can see here, the fractionation profile matched the analytical runs in that all 5 variant peaks from P1 to P5 were well separated. Now we can proceed to run the chemical mobilization to collect the fractions. So we'll use the same mobilization parameter as this map here. Here are the results of the icIEF analytical verification runs. We found that all charge variants were collected in 12 to 13 wells, and the purity of the purest fraction collected are between 80 to 100%. And for the DVD-IG, the two fraction experiment were performed. The fractions of the same identity were poured and divided into two portions. One for intact mass analysis, which we just analyzed directly without any sample prep. Now the other for reduced mass, in which the DTT is used. And both analyses use the regular standard flow LCMS system, and the injection volume is 10 microliter of the fractions or the reduced fraction samples. Now here are the intact mass results. The figures on the left are the TIC chromatograms of all the charge variant, and the right are their corresponding raw mass spectra. Now first we see that all 5 charge variant peaks were observed, including the least abundant one, P1, which has a 7.1% relative abundance. And the mass spectra on the right-hand side are all of good quality. Now from the spectra comparison, we see that the charge envelope of the bottom two, P1 and P2, were shifted when compared to the other 3 peaks of the P3, P4, and P5. Now here are the deconvoluted spectra. As you can see, the P3, P4, and P5 were characterized by a single peak at 200 kilodalton. So this is actually as expected for this DVD-IG. Now for P2, we see 2 peaks. First, we see a smaller peak of this 200 kilodalton, but we saw another peak, much stronger peak at 150 kilodalton. This will suggest that somehow for P2 is starting to kind of lose a 50 kilodalton unit to form a fragment at 150 kilodalton. Now for P1, we don't see anything of those 200 kilodalton at all. Only the fragment of 150 kilodalton was present. Now let's look at the region of those 200 kilodalton here. So this is a lineup of the spectra of the P2, P3, P4, and the P5. So you can see here, we clearly see a negative mass shift of the P4 and the P5 when compared to P2 and the P3. But for intact mass at such a high mass, the mass spectrometer did not have the resolution allow us to determine more precisely the mass shift. Then we move on to the reduced mass analysis. Here are the TIC chromatograms showing the light chains and the heavy chains. So in the middle are the deconvoluted spectra of the light chains. So you can see here for the light chains, for P2, P3, and P4, we don't see any of the mass shift. Now on the right-hand side are the deconvoluted spectra of the heavy chain. But for heavy chain, we can see here for P4 and P5, there is a mass shift of negative 18 daltons. So this negative 18 dalton modification has been identified in previous study as the aspartic acid to succinimide conversion in the CDR regions of the heavy chain. In summary, we have demonstrated that the new Maurice Flex can perform the icIEF-based fractionation in a single day, including method development, fractionation, and verification. Second, unlike the direct CEMS, the common icIEF reagent like methacellulose and urea can be used on Maurice flax without worrying about the sample matrix interferences with the mass spec. We also demonstrate that a single fractionation run provides sufficient high purity charge variant samples for intact mass or the reduced mass analysis. Lastly, the LCMS peptide mapping can also be carried out with the pooled charge variant fractions from multiple fractionation runs. Now, with the capability of analyzing the sizes and the charges, identity and purity, and now with the charge fractionation, we think the Maurice Flex has become a true CE-based multi-attribute analytical platform. I would like to take this opportunity to acknowledge the dedication and the hard work from our big team at the ProteinSimple San Jose site. We have been working really hard during the past 2 years to develop and launch the Maurice Flex instrument. Now, we also thank the analytical lab and the R&D systems at Minneapolis for running the LCMS analysis of the NIST-map samples. And lastly, we really appreciate the team led by Dr. Evan Herr at the AbbVie Bioresearch Center in Worcester for providing us the sample of the DVD-Ig for fractionation and carry out the intact and reduced mass analysis at their LCMS laboratories. Now, finally, I would like to thank you for taking time attending our webinar, and I'll be happy to answer any questions on the new Maurice Flex instrument.
Thank you, Dr. Wang. Let's jump right into our live Q&A. And we want to thank you for that informative presentation. Now to our audience, if you have any questions you'd like to ask, please do so now. Just click on that Ask a Question box located at the bottom of your screen, and we will answer as many of your questions as we have time for. Now, before I ask my first question to Dr. Wang, I would like to draw your attention again to the survey questions that we have on the left side of our screen. We would love your participation. So, Dr. Wang, let's dive in here. Our first question, is Maurice Flex going to replace Maurice?
The answer is no. The Maurice Flex is not going to replace the Maurice. And the Maurice Flex is just another member of the Maurice family. It can do all the other things as the Maurice do in analytical icIEF and CSDS. It's just simply add the new feature of the fractionation. Yeah.
Excellent. And can the Maurice Flex use the same cartridges used as Maurice? Used for Maurice?
Yes, I think for analytical assays, the Maurice Flex uses the Maurice icIEF cartridges. So that's included the icIEF cartridge, of course, and the CSDS cartridge, and also our last year's newly introduced turbo CSDS cartridge. So Maurice Flex can use all the existing Maurice cartridges. But for the fractionation run, Maurice we're going to use a new cartridge, a fractionation cartridge. Yeah, that's all. Yeah.
Excellent. What is the sample load for fractionation run on the Maurice Flex?
For the map samples, we have been using from depending on the different kind of a map. So we have been using around from 0.5 milligram to 2 milligram, depending on the map. Since the fractionation cartridge has a large diameter than the analytical cartridge, so the overall loading on the fractionation cartridge is much larger. So in our presentation, we show for the NIST map, for analytical run is only 0.1 microgram, and the fractionation cartridge is 6 microgram. So it's about almost 60 times higher than the analytical cartridge run. Yeah.
Got it. And can you repeat that volume of your cartridge of what it can hold?
the volume of the cartridge, I think for the analytical cartridge is around like a 0.5 microliter. For the fractionation cartridge, it's about 6 microliter. So the volume is much larger. Yeah.
Very good. And how many fractionation runs are needed for intact and peptide map analysis?
Yeah, I think this is a good question. So far, for the map samples we have tested, we probably tested about close to a dozen samples. We find that for intact mass, all the reduced map analysis, one fractionation run will provide sufficient samples for these kind of analysis. So here I want to emphasize that it's not like a one fractionation for both intact or reduced. You do one fractionation, that should provide enough sample for intact mass. You do another fractionation, and that will be enough sample for the reduced mass. So that's for the intact and the reduced mass. For the peptide mapping, I think we try here that because the sample prep are going to take more, require more samples. So we take 10 multiple fractionation runs to pull the sample together and to run this on the LCMS system. Yeah, with the standard LCMS system. Yeah, you can use less sample if you are run on the microflow or nanoflow. Yeah. Mm-hmm.
Thank you, Dr. Wang. And what is the maximum protein loading capacity for the Flex cartridge?
The loading capacity, it will depending on the map sample. So as I mentioned that the highest concentration we load is around like a 2 to 3 milligram per microliter, milligram per mil. So that's equivalent to like a 2 to 3 microgram per microliter. And then the total amount is 6 microliter is fixed. So we are looking at about 12 microgram to 18 microgram, something like that. Yeah, total.
Sorry, piggybacking off that, the examples presented use 6 and 2. Is there a way to estimate the optimal mass load for the fractioning run?
I think that you just need to try that, and then you have to during the method development, you need to. I think if you load too much, you need to worry about if there will be any aggregation of that. Okay, so you may need to add some of the more urea or something. So this is you have to play with that. But in general, we found that for the fractionation run, we use about like between most of the time between 1 or 2 milligram per mil concentration. Yeah.
Thank you, Dr. Wang. And it looks like we have a few questions that are going to require a little more follow-up that we'll be able to answer via email for our audience. Do you have any final comments for our audience?
Yeah, let me just read that one more question. There is a question for our users. They mentioned that they have already ordered the Flex cartridge. So they were wondering if you need to optimize the method to increase the protein loading from 0.1 microgram to 6 microgram. So I want to emphasize that for the analytical cartridge, the volume loaded is small. It's only around like a 0.5 microliter. So that's the reason you only loaded 0.1 microgram. So for the Flex cartridge, you have 6 microliter. It's already 30 times big. So if you load even the same concentration, you already load about 30 times more of that already. So you just need to, with the concentration, I would suggest to start with the 1 milligram per mil as the concentration for the map. Yeah.
Very good. We have another question coming here, but I'd just like to let all the audience know they're commenting, great question, Dr. Wang, and great technology on the Maurice Flex. Asking if this recorded seminar and presentation will be available on demand. And yes, it will be available on demand. Shortly, Labroots will send out an email letting you know when it's available for replay. And we do encourage you to share that email with your colleagues who may have missed today's live event. Dr. Wang, do you have any final comments for our audience?
Yeah, I think that if you continue to have questions, I think I will be very happy to kind of answer your questions. So I think with that, I have the emails on my last slide, so you can email me all the questions you want, and then I will really appreciate your attention. Yeah.
Very good. And yes, that slide is showing for our audience so they can see your email here. Dr. Wang, thank you again so much for your presentation today and your important research, your very insightful Q&A. I do want to thank our audience also for joining us today and for their interesting questions. As Dr. Wang mentioned, questions we did not answer today, and additionally those that are submitted during the on-demand period, they will be addressed by our speaker via the contact information you provided at the time of registration. Again, today's webcast can be viewed on demand, and Labroots will alert you via email when it's available for replay. Feel free to share that email with your colleagues. Thanks for joining us. Have a great day, everyone. Until next time.
Okay, thank you. Bye-bye.
Bye-bye.
Yeah.